One of the things that we've learned about the normal curve is that of what the empirical rule teaches us. In a normal curve, the bell-shaped curve like the one pictured here, we expect to find about 68% of all observations within a normally distributed set of data to be within one standard deviation of the mean. We expect about 95% of all data in a normally distributed set of data to be within 2 standard deviations of the mean. And we expect to find about 99.7% of all the data in a normally distributed set of data to be within 3 standard deviations of the mean. Now, when we're dealing with averages, we are not in the normal curve because we typically are dealing with a situation where we are using a sample standard deviation to estimate an unknown population standard deviation, which means that we are in a t-distribution. Now, depending upon the degrees of freedom of a t-distribution, it's going to look different, or it can look different than the normal curve. Let's say we're looking at a t-distribution with a small number of degrees of freedom. What we're going to see is that it's also very symmetric like the normal curve, but it's going to be flatter in the middle, and we're going to see a greater thickness in the tails out on the far left extreme and on the far right extreme. So when we're determining the critical value, let's say that this is the t-distribution with maybe 5 degrees of freedom. That means that 5 degrees of freedom. That means that we took a sample of size 6 and we calculated the average. Well, if I want to capture the middle 95% of this green t-distribution, I'm going to have to go further out than just 2 standard deviations like I would if I were in the normal curve. And that's because I have to recognize that this curve is flatter in the middle and fatter in the tails. So I'm going to have to go out a greater number of standard deviations to capture the middle 95%. And that will be true whenever I'm in a t-distribution, especially with those that are in a small number of degrees of freedom. For instance, if you pull up your table of critical values for the t-distribution, let's say that we're trying to determine the number of standard deviations from the center of the t-distribution that we need to go to capture the middle 95%. Now, that number of standard deviations is known as our critical value, which in many textbooks is referred to as T star. Well, if my level of confidence is 95%, and I took a sample of 6, which gave me degrees of freedom equal to 5. In my table of critical values for the t-distribution, in a normal curve, I would need to go out 1.96 standard deviations to capture the middle 95%. But in a t-distribution with 5 degrees of freedom, I would need to go out 2.571 standard deviations to capture the middle 95%. And again, I have to go further out in both directions, 2.571 below and 2.571 above, because of the fact that this t-distribution is so flat in the middle and so fat in the tails. So I've got to contain the middle 95%, which means I have to go out a greater number of standard deviations. Now, let's say instead that I was in a t-distribution that had 9 degrees of freedom. And I'm wanting to determine the critical value that would contain the middle 95% of that t-distribution. Well, again, looking at my t-distribution table of critical values, if I want to capture the middle 95% when I've got 9 degrees of freedom, now I would need to go out only 2.262 standard deviations to capture the middle 95%. So I'm still going out further in this t-distribution with 9 degrees of freedom than I would need to go in the normal curve, which I would need to go only 1.96 standard deviations out from the center to capture the middle 95%. Well, let's continue to increase our degrees of freedom. So let's say now that our degrees of freedom is 25. So we took a sample, say, of 26. And we want to know how many standard deviations out we would need to go in this t-distribution to capture the middle 95%. So I go to my table of critical values, and I go all the way down to 25 degrees of freedom for 95% confidence. And now I see I only need to go out 2.060 standard deviations from the center. So initially, with a smaller degrees of freedom, I needed to go out more than 2.5 standard deviations to capture the middle 95%. In a slightly larger number of degrees of freedom, 9, I needed to go out a fewer number of standard deviations, only 2.262 to capture the middle 95%. In this last example, in a t-distribution with a greater number of degrees of freedom, 25, I needed to go out just a little more than 2 standard deviations to capture the middle 95%. Well, let's go one step further, and let's say that I'm in a t-distribution where my degrees of freedom are equal to 100. So I took a sample, say, of 101 and calculated the average. Well, now you see that my T star, or critical value, for 100 degrees of freedom and 95% confidence is 1.984. Now, with an even higher number of degrees of freedom, significantly higher than 25, I have to go only 1.984 standard deviations out in both directions of the center to capture the middle 95%. It's getting very, very, very close to the 1.96 standard deviations that we know we would have to go out in the normal curve to capture the middle 95%.